In this section, we'll be looking at area under curve with respect to the x-axis. So the area between your curve and the x-axis. Now this is split into two different sections. One is area of a region above the x-axis. For a region above the x-axis, the area is bounded by a curve y equals to fx, the x-axis, and the lines x equals to a and x equals to b. Then it will be represented in this definite integral with your b and a being your x coordinates. Therefore, this definite integral just represents the shaded area that you see in the diagram above. Secondly, you have your area of a region below the x-axis. For a region below the x-axis, you have to add the modulus sign or a negative sign in front of your definite integral. This is because when you do your direct integration of an area below the x-axis, you will end up with a negative value. But you can never have a negative area, therefore, you need to make it positive by adding a modulus or a negative sign in front. And finally, if the question asks you to find points of intersection, we'll be using simultaneous equations. Now let's move on to some examples. So the diagram shows us this curve and gives us a point on the curve and tells us to find the shaded regions A and B. So first rule, whenever possible, use fixed shape formulas for triangles, squares, rectangles, or even trapeziums. So for instance, in area A, you realize that we can split it into two areas. This area on the left, we'll label it as A1, is simply the area of a triangle. And then the area on the right, we'll write it as A2, is the area that we have to use integration to find the value of. And finally, we just have our area B. Now, there's no need to split area B because it's a very simple integration between your x coordinate here and your x coordinate here. However, for area A, you have to split it and you cannot just integrate from x equals to 1 to x equals to 3 because by doing so, you will have an extra area of this part. Therefore, the only way to solve it is to split it up into this triangle and then this area. Now let's start solving. So we'll start with area A1. A1 is just, as mentioned, our triangle with our base from x equals to 1 to x equals to 2, which we can get from our point P given. Therefore, our base is just 1 unit, and our height is just the y coordinate of our point P, so 5 over 4. Therefore, it's just half times 1 times 5 over 4, which gives us 5 over 8 units. Now we have our A1. And to find A2, we'll use integration to get our area under curve from 2 to 3. So we have our upper bound of 3, lower bound of 2, and we have our equation of our curve. Then we bring the x up with the new power of minus 2. Then we just do our usual simple integration to get minus x plus 9x to the power of minus 1 over minus 1 within the square brackets, and then your bounds on the outside of the square brackets. As usual, sub your upper bound in, subtracted by your lower bound. Therefore, you get half unit square for your A2. Now to find your total area of A, we'll just sum up A1 and A2, which will give us 1 and 1 over 8 units square. Now for area B, we are integrating from x equals to 5 to x equals to 3. However, you will notice that area B is underneath the x-axis. So as mentioned before, when the area is under the x-axis, we have to add a negative sign or modulus to ensure that the area we get is a positive area. So we'll just include a negative sign in front and carry on with our usual definite integral. So upper bound of 5, lower bound of 3, and then our equation of curve. Afterwards, you don't have to reintegrate again because you've already done it to find your area A. So you can just use the result from above and then sub in your upper bound minus your lower bound, and you will get 4 over 5 units square for your area B.